So everybody gets really busy at this time of year, right? Like the homework is due, lab finals, or not lab finals, but the formals are due, and then you guys have midterms coming up probably. Yeah. So I like to tell you guys, stay focused. Don't get stuck on the obstacles. To stay focused on the goal. So I'm sure you guys all have a goal of like passing the course, right? So don't get caught up with, oh, I can't do this problem, or this concept is a little too hard. Just focus. If you here's the goal, right? And here's you. You want to keep looking at the goal. So like all these obstacles like come up in your way, right? And if you focus on them, sometimes you get stuck, right? So focus on the goal, right? It'll save you from frustration. Is everybody comfortable with derivatives? Has anybody not seen a derivative? If I write a derivative on the board, is anyone going to yell at me? I won't use them a lot, but every once in a while I'll add a little derivative here and there. So let's start today's lab, which is lab number 3. This is mostly on kinematics and acceleration. So we're going to do some bodies that are going to fall. We're going to measure their acceleration. But we have to talk about motion to understand acceleration. So velocity. Velocity is defined as the change in position over the change in time. You see me already starting to write the derivative, which is pretty self-explanatory because when you say velocity, like when you're driving your car, it's miles per hour, right? So it's a distance over time. Or in physics, we use SI units, so it'll be meters per second. You can also write that as dx dt, just means the time derivative of the position. Acceleration is the change in velocity over the change in time. And so if your velocity per second is changing, that means you're accelerating. So if you were at 0 meters per second, then you went to 1 meters per second, and then to 2 meters per second the next second, and then after that, you're accelerating. You can also write it with a derivative like that. So that brings me to kinematics equations. How many kinematics equations are there? Does anybody know? Four, yeah. So depending on which textbook you use, 4, 5, maybe 3. I say there's 4. And what do the kinematics equations help us to understand? You're saying it, motion, right? Motion. Yeah, so they help us to understand things in motion. And the first kinematics equation comes from the definition of velocity. We're just going to multiply both sides by delta t. And I'm going to get the change in x is equal to v delta t. It's too easy, right? So what does this tell us? Well, it tells us if you know your velocity and you know how long you've been driving in your car, you know how far you went. So if you're going 60 miles per hour and you drove for 1 hour, you went 60 miles. All right, the next kinematic equation comes from the definition of acceleration. I'm going to multiply both sides by delta t. Same procedure, and I get delta v is equal to a delta t. So if you're accelerating and you're given the amount of time that you're accelerating, you can find the change in velocity. Any questions so far? We're all good with this material? This is review, right? All right, the third one is a little bit harder to get. So I'm going to look at this equation here, and I'm going to write the final velocity minus the initial velocity is equal to a delta t. So I just wrote out the definition of delta V. And I'm going to move this guy to the other side. And then I'm going to do something funny. I'm going to write this guy, this velocity here, as dx dt. And the reason I'm doing that is because I want to know the change in position if I know my acceleration in time, not just if I know my final velocity, if I know my position, my acceleration in time. So how do you solve for x? Well, you integrate with respect to t, and we find that the change in x is equal to v naught delta t plus, how do we integrate delta t with respect to t? Remember? Yeah, so it's 1/2 delta t squared, and my acceleration is still there. So that's my third kinematics equation. Delta x is v naught delta t plus 1/2 a delta t squared. All right, you don't have to know how I got to it. All you need to know at the end of the day are what the equations are. All right, and so this one tells us our change in position when we're accelerating. This one was constant velocity, so we couldn't find our change in position with this when we were accelerating. And the last one I call the no time equation. V final squared is equal to V initial squared plus 2a delta x. All right, this one you use when the problem doesn't give you any time. So when you're reading the problem, you're like, oh, none of these work because I don't have the delta t. That's the only equation you have. So that's the one you use. Any questions? All right, let's take the scenario that you're falling under the influence of gravity. What's your acceleration when you're falling under gravity? Yeah, it's g, which is equal to 9.8 meters per second squared. Or minus g, if you, depending on whether you pick up as the positive direction. Let's pick down for the moment as the positive direction so I don't have to keep track of negative signs. So if I plotted versus time, my acceleration, what type of plot would I get? Yeah, a flat one. And what's the magnitude of it? Well, we just said it, right? It's g. So your acceleration isn't changing with time. That's what that says. All right, so let's do a different plot. Let's do velocity versus time. Now, is our velocity changing if we're falling? So if I drop this, so it started out with 0 velocity, and when it was at the bottom, it had a velocity. So obviously the velocity has increased. It's a change. Which sort of shape do we get? Linear. It looks something like that. By the way, what's the slope of this line? Yeah, it's 9.8 because rise over run is v over t, but v over t is the acceleration. So the slope is the acceleration. And the last one I want to do is position versus time. What does that one look like? Is it linear? No, you say no. Why? So the velocity is the derivative of the graph. Okay. So what you end up getting is what I got here, which is the third kinematics equation, which is quadratic in time. It's going to look something like this. So not quite linear. It's going to increase with time. All right, so those are the 3 plots. Any questions? All right, let's move on to the Atwood machine. So the average machine has a pulley that you put a string around, and then you hang some weights from. So here's a mass. Here is a smaller mass. I'm going to call this mass 2, and this one mass 1, because they're not necessarily the same mass. In fact, they'll be different. So mass 2 is greater than mass 1. All right, if mass 2 is greater than mass 1, what do you think this system is going to do? Yeah, so the mass 2 is going to move down, and mass 1 is going to move up. That's what we expect. All right, and just to be clear, I'm going to make this coordinate system with y being up. That's the positive y direction. All right, if we wanted to understand how this guy moves, what's something we could do to analyze its motion? You know, if I asked you, what is the acceleration of mass 2? How would we start to solve that problem? Figure out what forces are on it. So let's focus on mass 2, since that's the question I asked you, is what's the acceleration on mass 2, and identify the forces. So what forces are acting on this mass? Gravity, good. I'm going to call that F2 because it's on mass 2. So 2 goes with 2. Any other forces? Good, tension. So there's a tension. I'm going to make this guy a little bit longer. There's a tension force from the string pulling up, back up on the mass. All right. Any questions? All right, let's also do this for mass 1, since I like practicing our free body diagrams. And what do we have with mass 1? We also have gravity. And to differentiate it from this guy's force, I'm going to put F1, because it's not necessarily the same, because it's a lighter mass. And he also has tension pulling up. We call that T. All right, one thing I want to point out is that both of these are this. I labeled them both T because, T1 is equal to T2. So I could have called this T1 and this one called T2, but I didn't bother because I knew they're the same. Well, how do I know that they're the same? Is there any way to understand, make sense of that? So the reason I think they're the same is because this is connected by a string, and the string is not stretching. So by Newton's third law, there must be equal and opposite reactions, right? So if this force was bigger than this force, then the string would be like a rubber band. It'd be stretching. But strings don't stretch. They stay the same length. All right, what do we do after we have the free body diagrams? Okay, construct force relations. So I'm going to call that using Newton's second law. What's Newton's second law? Force is equal to mass times acceleration. And what type of quantity is force? It's a vector, so let's remind ourselves. And also acceleration is a vector. And this isn't just a force, this is the sum of forces. So I'm going to remind you guys of that by putting a big summation sign in front of it. All right, so for mass 2, what are the two forces that we're adding up? Well, it's tension and the force of gravity. So T, and since the force of gravity is in the opposite direction, I'm going to take care of its vectorness by putting a minus sign. Does everybody see that? These guys are in opposite directions. And then I'm going to say is equal to M2 A2. So this is focusing on this object. And then we can simplify this. What is the force of gravity on M2? It's mass times gravity, but specifically mass 2, right? All right, so we're almost there. Here's our acceleration on mass 2. Do we know mass 2's mass? Well, yeah, that's given. Do we know g? Yeah, that's 9.8 meters per second squared. Do we know the tension? Do we know that force? So we don't know that force, so we can't solve for acceleration quite yet until we find out what the tension is, in newtons. So what I'm going to do is I'm going to start analyzing this guy, because this guy also has tension in it. So if we sum up the forces on that guy, what do we get? We get T minus F1 is equal to M1 A1. And then T minus M1 G equals M1 A1. All right. If this guy is accelerating down and this guy is accelerating up, what do we know about their accelerations? How are they related? Okay, inversely, but mainly I want it not necessarily inversely, but they're off by a minus sign, because one's going up and the other one's going down. So they both have the same magnitude, but they're in opposite directions. So I'm going to replace this guy here with minus A2. Does that make sense? One's going up, the other one's going down. All right, so both of these equations have t, and both of them have our unknown, which is A2, which I'm just going to call A now because I don't want to keep track of the subscript. Just to be clear, there is a minus sign here. All right, so we have two equations and two unknowns. Can we solve the system? Yeah. Whenever you have if you have one equation, one unknown, obviously you can solve it. If you have two equations, two unknowns, you can solve it, and so on and so forth. So what I'm going to do is I'm going to solve this guy for t, and I'm going to plug it into here. So t is equal to, help me out, m2a plus m2g. And then I'm going to take this equation and I'm going to plug it in there. So we got m2a plus m2g, and hopefully all this works out, minus m1g equals minus m1a. All right, can we solve for a? I think we can. So we have, I'm moving this guy to the other side, m1a. This guy is plus m2a. I'm going to move these two to the other side. m1g minus m2g. All right, catch me now before if I made a mistake, because we're going to get the final answer. And if it's not right, it's going to be embarrassing. Did I do that right? He's nodding, so I'm confident. I'm going to factor out the a, because that's what we're solving for. So m1 plus m2 times a. And I'm going to factor out the g. m1 minus m2 g. And we're almost there. We just got to divide by this m1 plus m2. So a is equal to m1 minus m2 over m1 plus m2 times g, and that is what we're looking for. We found the acceleration. So now we know how m2 moves. What happens if I put a mass of 0 kilograms here? What's going to happen to this mass 2? It's going to accelerate down. How fast is it going to accelerate? It's going to free fall. Good. So it's going to fall at 9.8 meters per second. Let's check this formula and make sure I did it right. What if I put mass 2 is equal to 0? Mass 2 equals to 0. I get m1 over m1, which is 1. No, I set mass 1 equal to 0. Right? I set mass 1. So this guy's 0, this guy's 0. So I get minus m2 over m2, which is minus 1, times g. So minus g. Does that make sense? Yeah, because it's falling and it's going opposite of the positive direction, so it's falling at minus g. Okay? So I'm more confident that that's the right answer. Can we do any other scenarios to check it? What if the masses are equal? What will happen? If m1 and m2 are equal, physically, what's going to happen? Will the system move? Will it accelerate? No, we expect it to have 0 acceleration. If m1 is equal to m2, then these guys, this whole thing is 0, right? And so you get 0. Any questions? All right, so I'm going to quickly demo this. So I have a string on a pulley, and I have some weights here. We'll do equal masses first because it's easier. What do we expect with equal masses? No motion. All right, it's not moving, good. And if I make mass, let's call this one mass 2, a little heavier than mass 1. It accelerates, all right? Obviously, if I took the weight off of this guy would be in free fall, and it would fall at minus g. Cool? All right, you guys can get started.